Good morning, everyone. I think most of us have managed to join the meeting. So today we're going to start with a couple of practice problems. I want to make sure that we get in a lot of good practice before the next exam. I think that'll help us all to do well on the exam. So we're going to start out by looking at these three pictures of three scenarios. We got cells, we got ions, so the circles are cells. We've marked the concentration of each of these ions. We've also marked the membrane potential of the cell. So what I want you to do is each of those three images is tracking a specific ion. So for each cell, I want you to tell me on the left whether sodium is going to move in or out. So which direction the electrochemical driving force will be. And same thing for the potassium, same thing for the chloride ion. Because as we go through neurons, really what we're going to be tracking over and over and over again is the shifting of these variables, the membrane potential, the concentration, and therefore the electrochemical force. Okay, I'm going to go ahead and end that poll. Okay, so it looks like, I guess I can share the results with you. Sure, can I still see them? So it looks like we got a diversity of opinions. So I will tell you that the most common choice for each of these is correct. So sodium is going to move out, potassium is going to move out, and chloride is going to move in. So instead of having me talk, I'm going to ask someone to explain each of these scenarios to me. So does someone want to volunteer and tell me why they put that sodium would move out of that first cell? I know 22 of you put out. It is kind of 50-50, so maybe you all guessed, but I'm going to hold out hope. Someone's got a reason.
I think it is because that membrane potential was met and the plus 50 is beyond its electrical need. I think plus 30 was all that sodium needed.
So it is about the membrane potential. It's not really about comparing it to the equilibrium potential in this case, although it would affect the equilibrium potential. What we're looking at here in this image for sodium is that we can see the concentration of sodium on either side is the same, right? We have 30 millimoles of sodium outside the cell. We have 30 millimoles of sodium inside the cell. That means there's no chemical driving force on sodium, right? The chemical concentration on either side of this membrane is at equilibrium. But sodium is an ion. It's a cation. It has a positive charge. So what's happening in this first example is that we have a cell that's excited. So we have a cell that has a positive charge. And what happens with charges and ions is that like charges repel each other, opposite charges attract. So when we see that positive charge inside the cell, and we see that positive charge on sodium, we know that that positive charge inside the cell is going to repel the sodium because they're the same. So we're going to repel positive sodium ions away from that positive 50. So they're going to move out of the cell. Okay. We have something going on a little different with the potassium. Looks like people were a little more comfortable with the potassium. Who wants to talk about the potassium for me? So I'd like someone to talk about the chemical forces and someone to talk about the electrical forces. Okay, well, let's start with the electrical forces. Can someone tell me if the electrical force on the potassium in this second example, is that the same as the electrical force on sodium or is it different? Are we having the same sort of situation, or are we having a different situation? We have a positively charged potassium ion, and we have a positive membrane potential inside the cell.
So they're going to repel.
Yeah, exactly. That positive charge is going to repel the potassium. So our electrical driving force is out of the cell. Now, what about our chemical driving force? What's going on with our concentrations?
So concentration inside the cell is a lot higher. So it's going to move out of the cell.
Exactly. The potassium wants to move down its concentration gradient. So that chemical driving force is out of the cell from the area of high concentration to the area of low concentration. So this means that we have the chemical driving force going out and also the electrical driving force going out. So both our chemical and electrical driving forces are going out, which means our total electrochemical driving force, when we add these together, will also be out because there's nothing opposing them, right? Both forces are going in the same direction. Okay, so our final one are chloride ions moving into the cell. So someone tell me why they're moving in. Is it the chemical force or the electrical force?
It would have to be the chemical driving force because there is no electrical driving, like there's no membrane potential right now.
Exactly. Yeah. So we can see that there's a difference in the chloride concentration. We have a lot of chloride ions outside the cell, not very many inside the cell. So our chemical driving force is into the cell, but the membrane potential is 0. The cell doesn't have a difference in charge. So it's neither repelling nor attracting those chloride ions. So before we move forward with the rest of class, I also want to put in a quick promo for the McNair Scholars Program. It's a pretty cool program. So McNair works with you to get you paired with summer research opportunities and hopefully eventually get you into grad school. And they're accepting applications right now. Their first deadline is on October 15th. After the 15th, they still do accept rolling applications depending on how much space they have left. So you're eligible for McNair if you are a US citizen or permanent resident, if you are an income eligible first generation student, so like if your parents didn't go to college, you should apply, or if you're from any underrepresented racial or ethnic groups. They usually look for sophomores and STEM majors. I expect a bunch of you in this class are STEM majors, but any academic major can apply. And I encourage you to do so. I've seen some people's projects coming out of this, and it's really neat. It's a great opportunity both for resume building and for your own interest. So when we left off on Wednesday, we were talking about setting up the resting membrane potential for our neurons. And so what we had talked about thus far was potassium. And I actually set up a couple questions as a review for us on the stuff we went over on Wednesday about setting up that potassium part of our electrochemical forces. So I'm going to launch a poll on that as well. We'll go over this. Again, we're just doing practice, practice, practice. Okay. Okay, so we got a lot of different answers for this stuff with potassium. Okay, so we started out talking Wednesday about the function of the sodium-potassium pump. So when we were looking at our sodium-potassium pump, quick question, guys. Can you see both the poll results and the slides that I'm showing you, or only one at a time? Both?
I can see.
Okay, cool. So I'll pull up the slides that we're talking about as we talk about these answers. Except for we don't have the slide on the pump right now. Okay, so this way the sodium-potassium pump works is that what it's doing is we're taking 3 sodium ions, we're pushing them out of the cell, and then we turn around and we pull 2 potassium ions into the cell. This does have an effect on the membrane potential because this pump is not pulling in ions equally, right? We have 3 sodium going out. We have 2 potassium coming in. So we do call this an electrogenic pump because 1 additional charge on net is going out because 3 is bigger than 2. And as we move 1 positive charge out of the cell every time we run this pump, this makes the membrane potential negative. So that net export of 1 charge explains why both of these 2 first things are true about the sodium-potassium pump. Now, because we're exporting sodium, we're moving 3 sodium out of the cell, we are creating a high concentration of sodium outside the cell. So that's also true. As we run this over and over and over again, we're pushing more and more sodium out of the cell. What's not true is that we have a high concentration of potassium outside the cell. The place we'd have the high concentration of potassium is actually going to be inside. So as we're running this pump, we're pulling more and more potassium into the cell, which means it's building up inside the cell, and we're kind of depleting our external environment of potassium. So we're going to have high potassium in the cell and low potassium outside the cell. So D there would be our correct answer. This leads directly into question 2. So up here, okay. This slide you might not have directly remembered, but it looks like a bunch of people did remember that potassium gets through this membrane easier. We have more potassium channels, basically. So our cell membrane is way more permeable to potassium because of the presence of lots of potassium channels. So remember, because these are ions, they have to go through a channel. They can't go directly through the membrane. Only lipids could do that. Okay, so we have lots and lots of potassium channels. And when we looked here, talking about the potassium gradient that we're creating with the sodium-potassium pump, we just talked about the fact that we're pulling lots of potassium into the cell, which means we're creating a high concentration of potassium on the inside and a low concentration of potassium on the outside. So potassium is actually going to want to move out of the cell under these conditions. So the answer here would be A, or 1, or however these get numbered. My version doesn't have numbers. Okay. Our final question was about equilibrium potentials. So as we're talking about this membrane potential, we're also talking about what the equilibrium potential for each of the ions is. So we're trying to make sure that we all know the definition of an equilibrium potential. So true things about the equilibrium potential. At the equilibrium potential, the definition is that our chemical force is equal and opposing to our electrical force. So we have no net movement because those forces are pointing in opposite directions and we're stable. So both these first 2 things are actually true. So our chemical force is the same magnitude as the electrical force, which means that our total electrochemical force doesn't exist. It's 0, which means that we have no net movement of ions. So the ions aren't moving into the cell or out of the cell because we have these equal and opposing chemical and electrical forces. So all these 3 things would be true, the first, second, and last one. What's not true is that the solubility is going to change the equilibrium potential, specifically the lipid solubility. Because what we're talking about are ions. Ions are not lipid soluble because ions have a charge, lipids don't. So they basically repel each other. Okay. We'll do lots more practice problems in the future, just to make sure we're all prepped for the exam, because some about being prepared for the exam is just practicing the way questions are written and figuring out how to kind of apply the knowledge to the question. Okay. I guess questions about those things that we just talked about before I move forward. Sorry, I suppose I should have left up the poll questions. Okay, so that kind of got us through this review part of what we did on Wednesday. So we talked about equilibrium potentials. We're setting them up, and we're really tracking potassium and sodium. And what we're doing is changing how much negative charge and positive charge is on either side of the membrane. We know we're going to get to the point that we have negative 70 millivolts inside the neuron. We just should know that that is our resting membrane potential for neurons. Okay. So we talked about the fact that we're going to be thinking about gradients. We're going to be thinking about channels, because we're trying to set up a gradient in order to create a force on these ions. But we also have to have channels, because if we don't have a channel, the ions are charged. They can't move across that phospholipid barrier, because those phospholipids, they have that nonpolar section. They're going to repel anything with a charge. So we're going to need to have channels in order to allow the ions to move, in order to like release the force that we've been building up. So we talked about potassium first, because the membrane is more permeable to potassium. So the distribution for that potassium is that most of our potassium is inside the cell. That's where we have the buildup of the potassium. Outside the cell, we're going to see sodium and also chloride ions. Sodium is going to be the most important there. Okay. So we started with an example of how we're setting up the potassium membrane potential. So we saw if we start at 0 millivolts, but we run this sodium potassium pump, so we have this high concentration of potassium ions inside, potassium is going to want to move out of the cell down that concentration gradient. And in this imaginary example, we don't have to pencil in an electrical force yet, because we're starting at 0 millivolts. So we're starting with no difference in charges across the membrane if we're just tracking the potassium. Okay. So our chemical force is out. But as we move out, potassium is positively charged. So we're taking positives away from the inside. So if we are moving positive charges from the inside to the outside, what's left in the cell becomes more and more negative. So as the potassium moves out of the cell, we start to build up this negative charge inside the cell, which means there's now going to be a reverse pull on potassium back into the cell, because opposite charges attract. So once we do have a membrane potential, that charge, that voltage, is going to interact in some way with any ion we look at. So if it's negative, potassium is positive. This means we're going to have this pull on potassium back into the cell. However, our chemical force is still bigger, so potassium keeps moving out. It just slows down as we get more and more negative. So the chemical force is pretty strong. The electrical force starting out here is kind of weak. Okay. This keeps going until the cell reaches equilibrium. And this equilibrium potential, right, is where our magnitude of our chemical force and our electrical force are the same, but they're in opposite directions, so we have no net movement. So that's what we see here in this image. We see the chemical force, that's our yellow one. We see the electrical force, that's this blue one. We see that they drew those arrows the same size, but in opposite directions. So that's because the forces are the same magnitude, but opposite directions, which means we're at our equilibrium potential. The equilibrium potential for potassium happens to be negative 94. So that's like how negative the cell has to get in order for this electrical force to get big enough to make up for this chemical driving force. Like, I'm going to flip back for a slide for a second. So here we saw that this electrical force was quite kind of small at first. So something that affects the magnitude of the electrical force is how big that charge in the cell is. So the more and more negative the inside of the cell becomes, the harder and harder it's going to pull on a positive ion. So as we make the cell more and more negative, this electrical force grows and grows and grows. And when we hit negative 94, that equally opposes our chemical driving force. So this is going to be true for potassium specifically, this -94, because the chemical force that we're trying to oppose is the chemical force on potassium. So for any other ion, we'll have a different number, because any other ion is going to have a different chemical force, even though the electrical force is working on all the ions. So it's going to have a different number at which these forces are equal. Okay. So that's our equilibrium potential for potassium. I'll probably make you guys draw that at some point in the future. But right now we're going to move forward, just making sure that we remember that this equilibrium potential that we're talking about is where we have equal and opposing chemical and electrical forces, meaning we have no net movement and our electrochemical force is going to be 0. Okay. So the other part of our neuron that's really important, understanding how we're going to pass signals, is understanding the sodium equilibrium potential. So that's also going to affect our total membrane potential, and it's going to affect which way the sodium is going to want to move, which will have an effect on the action potential that we'll talk about probably next week. Okay, so we're going to start again with a hypothetical cell. So this hypothetical cell is permeable only to sodium. We're not going to be thinking about the potassium to start out with. Okay, so our ion distribution for the cell eventually is going to be that we have sodium and chloride outside the cell. Inside the cell, we have potassium and organic anions. But we're going to track just the sodium part first. Okay. So in this hypothetical cell, we had our sodium-potassium pump working at some point, right? But we're going to talk about the cell starting at 0 millivolts. So no charge there, no membrane potential. So no electrical force on any of our ions. But we are going to be thinking about a sodium gradient. Okay. So we have a buildup of sodium ions outside this cell. So we have a lot of sodium ions here. There are red ones, which means that we also have a chemical force on the sodium ions. So the sodium ions, they're going to go high to low. So that's always the direction we want to move for our chemical forces, high to low. Okay. So we're going to have a chemical driving force into the cell on the sodium. Okay. So when this membrane is permeable to sodium, that is the actual movement that we'll see on this ion. So our sodium, we're going to let it move into the cell. We're going to let it diffuse, saying it's permeable. This membrane is permeable to the sodium. Okay. As the sodium moves into the cell, sodium is positively charged. So it's bringing its positive charge with it. So the inside of the cell is going to be becoming less negative and more positive because we're moving positive charges in. As we move positive charges into the cell becomes more and more positive. This means it's going to get harder to pull positively charged sodium ions in because that positive charge is going to be repelling positively charged sodium. So just like we saw the electrical force developing for the potassium to pull it against its chemical driving force, we see the same sort of thing happening with the sodium. So as we make this cell positive, we create this electrical force working against our chemical force in the opposite direction because positive is going to repel positive. This means that we're going to have an electrical driving force on sodium moving out of the cell, okay? So this is going to continue until our cell reaches equilibrium. So the equilibrium potential, just like usual, is we have our equal and opposing chemical and electrical driving forces. So they cancel each other out. So if we add them together, we'd get 0. We're going to have no net movement of our ions. Now, the equilibrium potential for sodium is positive 60. So if we're tracking just sodium for this cell, that's how high we would get before we have an electrical force a big enough positive charge in the cell that we're repelling our sodium exactly as strongly as we are pulling it in with this chemical force. So you might immediately note that we have a different equilibrium potential for sodium than potassium, and they're actually different in polarity, right? They have different charges. Like sodium has a positive equilibrium potential, potassium has a negative equilibrium potential. So when we start thinking about the resting potential of our membranes and of our neurons, we're going to have to think about, well, how do they kind of share, right? Because in our normal cells, not these imaginary hypothetical cells, potassium is going to be trying to get to this negative number. Sodium is going to be trying to get to this positive number. So we're going to try and think about what effect these two ions are going to have on each other. But first, to summarize, our two forces acting on that sodium. We had the chemical force moving it in. So we got lots of sodium outside the cell, not very much inside. We have that electrical force moving the sodium out. So this is in the case where it's getting more and more positive, that electrical force is going to be resisting the chemical driving force. And when we hit equilibrium, our net force is going to be 0. So our electrical chemical force in these various phases, initially we have an electrochemical force moving in because we have a really strong chemical driving force. But then as the electrical driving force starts to build, because we're building a charge there, they're eventually going to come to be the same magnitude. Okay. So if we draw these together, we want to think about both the sodium and the potassium. What we're seeing here is basically the previous two figures kind of overlaid on each other. So we have our potassium in purple, we have our sodium in red, and we're tracking forces on both of them, right? So if we're looking at just the chemical driving forces on each of these ions, we see that we have high potassium inside the cell. So lots of this purple inside, which means our chemical force for potassium is from the inside to the outside because there's not really much potassium outside the cell. So it's going to want to move down its chemical gradient from the inside to the outside. The chemical driving force for sodium is from the outside to the inside. So it's going to be the opposite direction, kind of, right, than the potassium. So the potassium wants to move out, but the sodium wants to move in because we have a buildup of these sodium ions outside the cell. We don't have very many sodium ions inside the cell. So we've kind of depleted the sodium inside the cell. Okay. So this is like the beginning of our step for establishing the resting membrane potential of the neuron. So this imaginary cell here has both sodium and potassium, but right now it's at 0 millivolts. We haven't established the resting membrane potential yet. Okay. It makes sense that the chemical forces on these two ions are going to be in opposite directions because we remember that the sodium-potassium pump, which sets up these concentration gradients, pushes them in opposite directions as well. So that's one way we can remember what our chemical gradients look like, is if we remember the function of that sodium-potassium pump. Okay. So I'm going to give you guys partners right now, and I want you to discuss how you think the fact that the neuron is more permeable to potassium might affect the membrane potential. So we have a difference in permeability between our two ions. So does someone want to share their answer for something they think is going to be true about the movement of the potassium and how that might affect the membrane potential? But if you don't want to give your answer specifically about the membrane potential, just let me know something that's going to be true about our neuron because it's more permeable to potassium. Anybody want to say, Tovia? Yeah, great.
I thought maybe because the resting potential is negative 70 millivolts, where the equilibrium potential on it is negative 94. So it's so much closer, making it more permeable.
So the permeability is due to the fact that there are actually going to be more potassium channels, but you're absolutely right to key in on the fact that both our equilibrium potential of potassium are negative and the membrane potential is negative. So those two facts are linked. Does anybody want to tell me how they think that links work? Knowing that the fact that sorry, I'll reverse myself. So I'm telling you that this cell has more potassium channels and that there is a link between the fact that the equilibrium potential for potassium is negative and the membrane potential for potassium is negative, like Amanda just pointed out. Does anybody want to hazard a guess as to why we have that link? So what do you think is going to move more for this cell that's more permeable to potassium? Are we going to see more movement of the potassium or more movement of the sodium?
Potassium.
I would think more potassium.
Yeah.
Because it's happening faster.
Yeah, so the fact that this membrane is permeable to potassium more than sodium means that the potassium is better able to move around, which is actually how we're going to end up with a membrane potential that's closer to potassium's equilibrium potential than it is to sodium's equilibrium potential. So the fact that the potassium is better able to move has a real effect here on the membrane potential. Okay. And we're going to look at the steps for this. Okay. So here's our facts that we know, right? Our membrane potential is more permeable to potassium. So what we see here in this figure, our potassium was purple or blue or whatever color this looks like to you. And so are our potassium channels. So they're this purple blue color. We can see
I don't
that
see your screen.
Oh,
I'm sorry.
did I unshare? Thank you. No, absolutely. Thank you for butting in and telling me that.
There we go.
You know?
Yeah.
Great. Okay. So our first fact that we know is that our membrane is more permeable to the potassium. So we can see here that we have 3 channels drawn in that are the same color as our little potassium ions. This is to emphasize that there are more channels for the potassium than there are for sodium. So sodium was the red one. So we can see that we've drawn on just 1 channel for sodium to represent our sodium channels, but we drew on 3 for potassium because this cell is more permeable to potassium. So in reality, it's 25 times more permeable to potassium, but that would make this picture really messy. So just focus in on that more versus less rather than the specific number. So this means that when we set up these concentration gradients for the potassium and the sodium, the potassium is better able to move. Like it can move faster because we have more channels. So we talked about affecting the rates of transport when we were talking about transport in our last unit. We talked about the fact that basically if we have more doorways in the cell, if this membrane is more permeable, in this case, that permeability is due to these more channels, that means that we'll have a faster rate of movement. And so that's true for the potassium here. We have a faster rate of movement because we have more channels, making the membrane more permeable to potassium. So more of our potassium is leaving than our sodium can get in because there aren't that many sodium channels. So they're full, right? We can only let in 1 sodium at a time. So the movement of the sodium is slow, which means that here in this picture, right, we'd have 3 potassium get out every time a sodium gets in. So we're going to have a net export of charges just because of this permeability, just because more positive charges can escape. then positive charges can get in. So this is due to the potassium chemical gradient and the permeability of the membrane to the potassium. So in order for this export of charges to make this inside of the cell negative, we have to have both factors. We have to have the forces that set up this situation so that potassium wants to get out, and then we have to let it get out using this membrane permeability using those potassium channels. Okay. So this makes the inside of the cell get negative, even though we have some sodium coming in. So sodium is bringing positive charges into the cell, but it can't do it very quickly. It's doing it pretty slowly because there just aren't that many channels. So even though sodium is able to follow its gradient, right, it is going from this high to low into the cell, it can't make up for the fact that all these positive charges are escaping in the form of potassium. Okay. So when I'm just emphasizing this because when we went through our example for just sodium, we saw that the inside of the cell eventually became positive. But when we're talking about our resting membrane potential of neurons, our cell is going to be negative, not positive, because the potassium is escaping so fast. Okay. This is leading electrical forces to develop. So our electrical force for both of these ions, because both of these ions are positively charged, as the inside of the cell becomes negatively charged because potassium is escaping really fast, this means that the electrical force for both of these ions is pointing into the cell. Because remember, the electrical force, it doesn't care if you're a potassium ion, it doesn't care if you're a sodium ion. What it cares about is what kind of charge you have, so that polarity, the positive or negative. And it cares about like how charged you are, so the valence, so like whether we have calcium 2+ or just our sodium plus, our potassium 1+, you know. So we have our sodium and our potassium both attracted to this negative charge. Okay. So when we add in this electrical force to our existing chemical forces due to our chemical gradients, our electrical force for potassium here at the top is pointing in the opposite direction from our chemical force on potassium. So they're opposing each other. So as this electrical force builds on the potassium, the movement of potassium in total, so our electrochemical combination driving force, decreases. So this is going to slow down. So potassium is going to escape more slowly as this electrical force builds. But something different is happening with our sodium. So if we look here at our gradients for sodium, the chemical force for sodium is in. And in our example with just sodium, we produced an electrical force that was opposing sodium. But now that we're tracking both, the potassium and the sodium, our electrical force for the sodium is also pointing in. So our chemical force for sodium and our electrical force for sodium, as we're building towards our resting membrane potential for a neuron, are pointing the same direction. So they kind of like speed each other up, right? This is starting to snowball a little bit because our chemical force and our electrical force both point in the same direction. So now when we add them together, we get a bigger number rather than a smaller number because they're in the same direction. So as the electrical forces build up, we increase the force, the total force, our electrochemical force on sodium, but we decrease the force, we're weakening this force on potassium. Okay. So